Cardiovascular Physiology, Hemodynamics. Welcome to today's podcast, where we dive into the fascinating world of hemodynamics, the science that unravels the physical principles behind blood flow in the cardiovascular system. Imagine hemodynamics as the physics of circulation. It unlocks the secrets of how and why blood moves throughout the body, not just its final destination. At the heart of hemodynamics lies a fundamental principle, often referred to as the hemodynamic triad. This principle is best described by an equation that mirrors Ohm's law in electricity. Blood flow is equal to the pressure difference divided by resistance. This relationship forms the cornerstone of our understanding of blood movement. Let's break down these three essential components. First, we have blood flow, the amount of blood passing through a vessel or the entire circulatory system over a certain period. The total volume pumped by the heart is a critical measurement, as it determines the oxygen and nutrient supply to tissues. Next is the pressure gradient. Blood moves from areas of higher pressure to areas of lower pressure, and it is this difference, rather than the absolute pressure, that drives circulation. For example, the pressure difference between the aorta and the right atrium propels blood through the systemic circuit. Locally, it could be the difference between the start of an arteriole and the end of a venule. The heart is responsible for generating this pressure, with the highest values found in the aorta during the contraction phase and progressively decreasing until nearly zero in the right atrium. Mean arterial pressure, or the average pressure within the arteries during a full heartbeat, is the primary force that ensures organs are properly supplied with blood. Without a sufficient pressure gradient, blood cannot flow, and vital organs risk being deprived of oxygen, an issue commonly seen in circulatory shock. The third key player is resistance, the opposition encountered by blood as it moves through vessels. Resistance is not a static value, it is dynamically influenced by several factors, and its regulation is crucial for controlling blood flow. According to Poiseuille's law, resistance is determined by blood viscosity, the length of the vessel, and most importantly, the vessel's radius. Let's focus on vessel radius, as it is the body's primary tool for adjusting blood flow. Because resistance is inversely related to the fourth power of the radius, even a slight change in vessel diameter leads to a dramatic change in resistance and, therefore, flow. For instance, if a vessel's radius is reduced by half, resistance increases 16 times, making it much harder for blood to pass through. The nervous system, local chemical signals, and hormones all work together to constrict or dilate blood vessels. Fine-tuning resistance is needed. Viscosity, or the internal thickness of blood, is mainly determined by the proportion of red blood cells. When viscosity increases, such as in conditions like polycythemia or dehydration, resistance goes up and flow is reduced. On the other hand, decreased viscosity, seen in anemia or excessive dilution, lowers resistance and boosts flow. Vessel length also influences resistance. Longer vessels create more opposition to flow. While this factor remains constant in adults, it helps explain why increased body fat, which requires a greater network of capillaries, can contribute to high blood pressure. Now, let's explore the types of blood flow. Laminar flow is the normal, smooth movement of blood, where layers glide past each other silently. The outermost layer, closest to the vessel wall, moves slowest due to friction, while the innermost layer moves fastest. In contrast, turbulent flow is chaotic, characterized by swirling currents and eddies. This type of flow can occur when blood velocity is high, vessel diameter is large, viscosity is low, or there are irregularities in the vessel wall, such as a plaque. Turbulent flow creates audible sounds, known as bruits, which can be detected by a stethoscope over narrowed arteries. The speed of blood movement, or velocity, is distinct from the volume of flow. Velocity is determined by dividing the flow by the cross-sectional area of the vessel. The total cross-sectional area of the vascular network is crucial in setting the velocity. In the aorta, where the area is relatively small, blood moves swiftly. However, when blood enters the capillaries, tiny but vast in number, the total area increases greatly, resulting in a dramatic slowdown. This slower movement is essential, as it gives time for the exchange of gases, nutrients, and wastes between blood and tissues. Wall tension, described by the law of Laplace, is another physical factor to consider. It is calculated by multiplying pressure by vessel radius. This law explains why larger vessels and heart chambers need thicker walls to withstand greater tension. In clinical settings, such as after a heart attack when the ventricle becomes enlarged or in the case of an aortic aneurysm, The increased radius means the wall must bear more tension. If the wall is weakened, rupture or failure may occur. To summarize, the cardiovascular system is a dynamic and integrated network. Understanding hemodynamics is essential for grasping how blood flow is regulated. For example, during exercise, metabolites produced by active muscles cause blood vessels to widen, dramatically lowering resistance and increasing flow to those tissues. To maintain overall blood pressure, the body may constrict vessels in non-essential areas, raising total peripheral resistance and helping to sustain mean arterial pressure. In essence, hemodynamics reveals the elegant physics behind the circulatory system's ability to efficiently direct blood to where it is needed, precisely when it is needed, by balancing pressure and, above all, resistance. Thanks for tuning into today's episode. If you enjoy the content, please like, share and subscribe. It's the Everything Surgery Podcast. Dissect the extraordinary.